In this tutorial, we're going to talk about gravitation at the surface of the Earth. Most of you would be familiar with Newton's law of gravitation, which he described in his masterpiece, Principia. We have the force of gravity is equal to g, which is the gravitational constant found by Cavendish, times m1, m2 over the separating distance squared. This value of g by Cavendish right here was found to be a very, very small number via the torsion bar experiment we've seen in class. This, of course, is given to you on your equation sheet. It's going to be 6.67 times 10 to the negative 11. The units are a little bizarre. Newtons times meters squared over kilograms squared. And what's important to do in a problem where you're dealing with a question about gravity is to basically set this gravitational force that we've just described as the net force. And so we get Fg is equal to F net. That's the net force for some object on the surface of the Earth. So if we were to draw a free body diagram perhaps of some object right here at the surface, the only force acting here would be this gravitational force. So the net force is the gravitational force. And so I'm going to basically substitute in for net force mass times acceleration. This is Newton's second law. And then for the gravitational force, I'm going to basically plug in that expression from Newton, also from Newton, I should say. So I end up getting g times m1, m2 over r squared is equal to the mass of the object, let's call it object number 1, times a, where this is object number 1, and let's say that the Earth, or the center of mass of the Earth, is object number 2. We can see that the masses of the object cancel out, and just through that stroke of the pen, we can see that mass doesn't affect the acceleration on the surface of the planet. And I get g times m2, in this case the mass of the Earth, divided by the separating distance squared, which is r. So if I were inclined to take a look at this separating distance, this is the radius of the planet r. And in a problem like this, if this is r, then this expression is sufficient. Now, there's a couple of trick questions here that can be asked. One of them is, what's the acceleration 10,000 meters above the surface? And so if we had some big mountaintop here, I've kind of drawn that surface feature on the sketch here, we can see that r changes by a little bit. And so therefore, technically, the acceleration does go down as r goes up. We can see that relationship here, but not by that much. As a matter of fact, when completing orbits, I'm thinking of John Glenn, the first American to complete orbits, even though he's going very fast side to side here, that might be his tangential velocity at the moment. He had about 98% of Earth's gravitational acceleration at that altitude above the surface of the Earth. Keep in mind that this value of r for Earth is about 6,400 kilometers or so. And so if I were to convert that to meters, of course, it'd be, over 6 million meters. So increasing the value of r from 6 million and then adding 10,000 meters to that doesn't really change the value of our acceleration very much. So in these types of problems, it's important to keep that in mind. However, if you increase the value of r by some substantial amount, so perhaps now we're at double the radial distance away here. So I'm going to draw some point, let's call that point A, out in free space. And let's say that this separating distance between point A and the center of the Earth is equal to 2r. In a situation like that, we can see now that does have a profound effect on the acceleration. So if I increase the bottom here by a factor of 2, it becomes 2 squared. And the top is just a constant. It's the constant g times the mass of the Earth. And so we can see that that's going to have a pretty substantial effect. I've increased the value of the bottom by a factor of 4, and we can see then that the acceleration goes down by a factor of 4 in a situation like this. So when you're asked about gravitation at the surface, you need to keep in mind that we're just setting Newton's law of gravity equal to Newton's second law. And for the most part, the acceleration stays near that surface value unless you increase some substantive distances away in terms of, I would think, in multiples of the radial distance.